Ferenczi. And Beverly Light, who is a student of Madrid. Okay, so how do we begin? So the starting point is to look at a definition which came up in several talks, for instance, in Dani's talk. So we say that a real number alpha is badly approximate. If the following thing happens, if there exists a constant C positive for which the inequality alpha minus, say Q alpha minus P bigger than or equal to C over the absolute value of Q holds for all, so we can actually just have natural numbers. So natural numbers Q and integers P. So I remind you quickly that so we learned in Wernicke's talk about Dirichlet's result, Dirichlet's theorem, a corollary of which guarantees us that for all real numbers we always have approximations of the following qualities. And so these are numbers which while they satisfy this inequality, so this is true for infinitely many P's and Q's. So these are numbers which, while they satisfy this inequality, they somehow violate the inequality as well in this particular sense. And what do we know about these numbers? So some facts about these numbers are that, first of all, they have, there are not so many of them in sense of Lebesgue measures, so have Lebesgue measure 0. On the other hand, it turns out that if you are willing to be a bit more flexible about your notion of size, there turn out to be quite a few of these numbers. So in particular, they have a full Hausdorff dimension. And it turns out that this is in fact a consequence of an even better property, which I'm now going to describe. So this property is going to be called the following. So let me denote by BAG, the set of badly approximable numbers. And so it turns out that this set BAG is what is called a winning set for a game. So which was introduced for this purpose by Wolfgang Schmidt. So it goes by the name Schmidt's game. So this game is actually very easy to describe, so let me quickly do that. So what happens in Schmidt's game?
Anish, is that inequality at the top of the right-hand blackboard correct? Is that what you meant?
Yes.
That's so well approximate.
No, so this is true for every real number.
Every real number?
Yes.
Okay. So
it's a consequence
what
of
has the Lebesgue measure 0?
So those numbers which satisfy the other way around for every PQ with a constant.
Okay.
That is the measure.
Okay.
What can you do?
So just to avoid confusion, let me actually erase it. So this is no longer very clear. Okay, so how do you play Schmidt's game? So what you do is you start with a complete metric space, say X, call it X. You start with two players who go by various names. So I call them A and B. So I think Kleinbach and Baroda call them Alice and Bob. And sorry?
Schmidt called the black and white, and the editor of the journal said they should be called Alice and Bob.
Ah, I see. So it's probably not politically correct to say black and white anymore. So let's just call it A and B. And it has two parameters, alpha and beta. And the game proceeds in the following manner. So what A does is he picks a ball and call it A0 inside this complete metric space. And then it's B's turn. So what B does is B picks a ball, say B0, with the restriction that the ball has to be contained in A0's ball. And moreover, that the radius of this ball has to be alpha times the radius of the ball, which A0 is A0. And then A picks a ball inside B0, call it A1, whose radius is now alpha beta times, and so on and so forth. And so this game continues forever. So now it's a complete metric space. So at the end of it, when you end up with one ball. Oh, of course. So I forgot to mention that you also have a set. So let's call the set say W. So since it's a complete metric space and a sequence of decreasing balls, so at the end there is one point, say X0, and we say that B wins, or B is a winning strategy if this point X0 happens to belong to this set. So in typical examples, you play the game on the real line, and W will be the set of vaguely approximable numbers. And if B wins the game, then the last point should be vaguely approximable. Right, and so B wins if B wins if X0 belongs to W, and in this situation we call W alpha beta winning. So a couple of more terms. So so we say that W is alpha winning if B can find this strategy for all if W is alpha beta winning. For all betas between 0 and 1. And we just simply say it's winning if it's alpha winning for some alpha. So I should mention that in the set theory community, there's a long tradition of studying games like this in the logical category. So there is a work of Stobie and Ulam and so on and so forth. Schmidt was responsible for introducing games into number theory, and Dani was responsible for bringing games in the Gmod gamma business. So before I state all that, let me say some nice properties of winning sets. So one property is, of course, as you would have guessed, so these sets are thick, so winning sets are thick, which means that if I intersect them with open balls in Rn, they have full loss activity. So there are other nice properties. So for example, if I'm able to show that something is alpha winning, then I can take countable intersections of alpha winning sets. Are alpha winning, which is really nice, and will be used when I state our result. And The third property is that, right, so winning sets are preserved under bi-Lipschitz homeomorphisms. I'm not going to have time, so I should just mention one thing, which is that, so the next thing I'm going to discuss is Dani's Krella paper in 1985, and after that there's been a sort of, a lot of progress in this business, and so I'm not going to have time to cover most of it. I'd just like to make one point, which is that, there are variations on Schmidt's game introduced by several people. For example, there's a variation due to Kurt McMullen, which actually significantly relaxes this assumption. So he has a variation where you can actually map these winning sets under quasi-isometric, which is a much nicer problem. Right, okay, so that's the setup, and now I'm going to go back to, as I said, what nowadays is called the Dani correspondence. So what we want to do is try to interpret the property of being badly approximable in a suitable homogeneous space. So the homogeneous space is going to be G factor gamma, where G is SLN R. So matrices with determinant 1, gamma is SLN Z. And as we know quite well, we can identify G factor gamma as G spaces with the set of unimodular, which means area 1, lattices in Rn. And so Dani found a nice way of interpreting how to look at badly approximable numbers in terms of certain flows on this space. So let me explain how that goes right now. So just for simplicity, let's just look at the case of SL to R factor SL to Z. So what we do is we start with the real number alpha. And with this real number alpha, we associate a unimodular lattice in the following manner. So I just embed alpha in the upper right corner of this matrix and look at the point on this non-compact space. So this is a non-compact space. And so this gives me a point on this space. So let me call this U sub alpha. So this point, so this U sub alpha. And so what Dani showed was the following. So Dani showed that the proposition. So let me just set up the notation. So we have seen these flows a lot recently. So this is a diagonal flow. I'm going to look at the positive part of the orbit. And of course, this is the geodesic flow on the unit tangent bundle of the modular surface. So what Dani showed is that alpha is badly approximable if and only if the GT orbit of this point U sub alpha is bounded in SL to R factor S. GT is and so in fact now the question arises, well, okay, so the GT orbit, so the GT action on this space is ergodic and mixing and so on and so forth. So the bounding orbits obviously have zero measure, but this shows using this correspondence they're in fact winning for Schmidt's game. So some remarks about this is that first of all, I should say that I'm just stating it in this special case. It was much more general. But in a subsequent paper, Dani generalized this. So this happened in this Krella paper, and in a subsequent paper, which Dani showed the following. So he generalized this phenomena of abundance of bounded geodesic orbits to R rank 1 semisimple Lie groups. So if G is a connected R rank 1 semisimple Lie group, gamma is a lattice in G. Then essentially the result is as follows. So what you should do is you should take one parameter subgroup which goes by the name non-quasi-unipotent. So what this means simply is that if you look at the adjoint of say G1, which is a linear transformation, then it should have an eigenvalue whose absolute value is not 1. So it's the right generalization of this kind. Then bounded. So I'm not making a very precise statement. So, but essentially what he shows is that bounded GT orbits are with. And the consequence of this is that if you look at bounded geodesic orbits, in complete negatively curved Riemannian manifolds of finite volume, then they're also winning. So to do this, you just take G to the SON1. And so the result that I'd like to mention now, which is going to be relevant to our theorem, is this was further generalized in two papers by Aravinda and Loisen. So again, I'm not going to write down the complete result, but essentially what they prove is that if you look at points on C1 curves in such a manifold, or more generally in the rank 1 locally symmetric space, whose orbit is bounded, and they also are big. Right, okay, so this is part one of the story. So our theorem with Manfred and Beverly combines 2 or 3 themes, so this is part one of the theme. Now the second part of the theme goes back to the definition of Baddeley approximable, so let me quickly run through that. So you can generalize this notion of Baddeley approximable to higher dimensions. Okay, so actually let me just point out 2 things which are important in this context. So this is a good place to do it. So Dani's work actually led to Margulis making some very precise conjectures. So Margulis' conjecture on bounded orbits in an ICM US. Due to lack of time, they're very interesting and nice conjectures. I won't be able to state them, but let me point out that one of them was solved by Kleinbach and Margulis. So you would guess what the conjecture is. you take Dani's theorem and try to replace R rank 1 by general solution. And the second conjecture was very recently solved by Kleinbach and Baroda. So, unfortunately, I won't have much time to discuss these quite significant developments. Instead, let me try to generalize the notion of badly approximable numbers to higher dimensions. So, here is a natural way to do this. So, you could call a vector, say, alpha, badly approximable if there exists a constant C positive such that the maximum taken over the coordinates of q times alpha I minus an integer vector pi is at least the C over q for every integer vector p in Zn and q rational. And so you can actually, everything that I said about badly approximable numbers is essentially true. The full house of dimension.
Q to the power 1 over n.
Sorry?
Q to the power 1 over n.
1 over n. Ah, yes, that's an important thing. So, so now what you can also do is you can have a weighted version of this. Weighted add. So in order to do this, what you do is you look at a set of weights. So these are real numbers, n of them, who sum up to 1. And you call alpha r badly approximable if the same thing is true, but instead of this 1 over n, I say put a 1 over ri. Right? And so again, Kleinbach and Barak have lovely results about how many of these there are and various properties of it. So for a long time, it turns out, so it's turned out to be surprisingly difficult to study these sets. In particular, for a long time, there was an open conjecture due to W. Schmidt, which has been resolved by Badziahin, Pollington, and Vellani quite recently, which simply ask the following question. Suppose I take two distinct R's, say even an R2, and intersect these sets back R, do I get anything or not? Just simply that. So it turns out that, in fact, under certain hypotheses, which I don't want to get into, what these three gentlemen proved is that the intersection of these two sets, for example, has full Hausdorff dimension. So the interest in this conjecture was due to the fact observed by Schmidt that that if you actually could manage to show that this conjecture was false, then you would get a proof of a still open conjecture, which is Little's. But thankfully, or rather, I don't know, thankfully or not, his intuition turned out to be correct. Okay, so so far we've covered abundance of bounded orbits and Schmidt's conjecture. And the last theme to discuss before I can state the theorem. So the last theme has to do with what goes by the name Diophantine approximation on manifolds, which we heard about in Bernick's talk. So what is this subject about? It's actually very easy to understand. So let me just, instead of writing various things down, try to convince you using pictures. So the subject is as follows. So I have, so I know various things. So for example, I know numbers which are very well approximable, or vectors in R2, have zero measure. I know that badly approximable vectors have zero measure, but also have full dimension. And the question is very simple. If I take a one-dimensional curve or a variety, can the same be said for points on this variety? So this is a little bit different from what Amos was discussing, because as he pointed out, in this business we are approximating by depending on which form of approximation you do, but essentially the points are not, the rational points don't have to lie on the curve. So this is not an algebraic thing, it's more of a topological thing. So the right condition for a curve to satisfy the property that it inherits, a property like this from R2, is that it somehow avoids a fine subspace. So I'm going to say, I'm going to call a curve which avoids affine subspaces non-degenerate. If I have time at the end, I'll give you a precise definition, but for now, I'd like you to just think of the parabola. It's a good candidate for a non-degenerate curve. Right, so what have we proved? So our intention was somehow to try to combine these themes into a single thing, into a single result. So let me state it. So K is going to be a number field. And S is going to be a set of infinite places. And so Ks is going to be the product of these completions. So K sigma sigma S. So think of this as some Euclidean space. And of course we have an embedding of K into K sigma. And so let me first state the result, and then I'll try to give some more context to it. So G sub t for me is going to be the diagonal, which is simply e to the t, e to the minus t. And so since I'm a little short on time, I'm going to state the general result. So I'm going to, just as before, pick a vector R of weights. Rd, where d is R plus 2s. I'm going to look at the weighted diagonal orbit. So at each space I have this this weight. So let me index it by the place. So it's R sigma t to the minus R sigma t, and sigma varies over all these weights. And so the theorem is. So what I'm going to do is I'm going to take analytic maps, phi sub sigma, from the unit interval. So I'm going to take a collection of these. So sigma is in S. And the collection of these, so this is going to land in Ks. The analytic maps will satisfy the following condition such that, so if I look at the collection of them, phi sub sigma, I get some analytic curve in Ks. And this curve such that they are not parallel to d over 2 or more coordinate axes. Then
These are plus 2s?
sorry?
These are plus 2s? What is it?
These are. actually, so that's when there are some more mild hypotheses which should be made away from zero and so on, which are unhelpful to states. Then, so that phi of x be the matrix 1 phi sigma of x, 0, 1, sigma. And so the result is that then for every lambda in SL2 KS, so SL2 KS is just a product of SL2 K sigmas, and I have an actual arithmetic lattice which is SL2 of the ring of integers of the number field embedded diagonally. Then for every lambda in SL2 KS factor SL2 OK, the following is true. The set of numbers x in 0, 1 such that GRT lambda, so phi x lambda is bounded, is really so this is part 1 of the theorem, and second part is moreover. So the winning comes with an alpha, and the alpha is independent of the weight. Okay, 7 elements. Okay. So this is the main theorem, and let me list some quick corollaries, and then I'll stop because I know everyone's quite happy. So this is the main theorem. So some corollaries. So I didn't mention, actually, I don't have time, but so the business of approximating points by things in ratios of integers and number fields is quite well developed. So there are various people, I just mentioned some names and stuff. So there is a gentleman called Vadodara, there is Berger, there is Maharaja. All of whom have sort of given versions of Dirichlet's theorem and badly approximable in this setting. And so the main tool here is a nice, a very nice idyllic interpretation of Minkowski's theory due to Bombieri and Waller. So it would have been natural for me to say a little bit about this because I'm talking about badly approximable numbers from vector fields and without talking about Dirichlet's theorem, but it's just a matter of time. Okay, so corollaries is that, say that alpha in Ks is K badly approximable. If the following is true, so we make the same definition. So I take the maximum over I. This is a vector, so I look at a sigma of P. So let me index alpha also by sigma plus sigma of Q alpha of sigma is at least, if there exists a positive constant, such that this is at least a constant times the maximum over sigma of sigma of Q. So this is just one possibility of how to define it. You could replace this by the norm of Q or even a suitable height, and everything is pretty much the same. And so the corollary of that is that the set of x in 0, 1, for which phi of x, where phi is the analytic curve in the theorem. So I said this is phi of x. So let me not. That's not what I mean. So let me say that. So psi of x is a collection of phi sub sigma, such that psi of x is is k bad is winning. So you can slice, there's a nice tool called Masterton slicing theory, to conclude that k bad itself is winning, which doesn't seem to be known, but I'm very confident also follows from some things that Kleinbach and Barak have done. And more significantly to the issue at hand, you can, since the alpha is independent of R, you can take countable intersection. So once you show that k bad is winning, of course you also have a weighted k bad, so k bad R is also winning. And countable intersections of k bad R are also winning. So this way we get a number field envelope. And I'll conclude on one note. So what we showed is that if you take these weighted guys, then the orbits with bounded trajectory are winning. But it's quite important and striking to note that, as for example, if I simply looked at something like SL to R times SL to R factor SL to, say, z square root of 2. And I look for bounded trajectories of the full diagonal, so the full, so e to the t, e to the minus t, e to the s, e to the minus s. You could ask why I'm not looking at these, because these are natural. So it's a consequence of a theorem of Lindenstrauss that in fact the set of bounded trajectories under this has zero Hausdorff dimension. So in some sense, you can get a lot of points which are bounded under these weighted orbits, but the moment you go to the full thing, there's zero Hausdorff dimension. I'll stop.
So we break for lunch now and meet again here at 2:30 for further classes.
The final lecture of the final day. So the